be talking through the solution to question 4 from the 2015 examination paper for Massographics and Virtual Environments. So question 4 describes a situation where you've got a projectile which is fired at an angle of pi/4 from the horizontal with an initial velocity of 10 meters per second. We're assuming the acceleration due to gravity is 9.81 meters per second. Okay. So, briefly explain kinetic and potential energy. Kinetic energy is energy possessed by a body in motion, and it is described by a half times n times v squared. If v is a vector, you find its magnitude and square it. If it's just a quantity, you just square it. M is the mass of the body. Potential energy is energy possessed by a body due to its position. So, for example, if we raise an object up off the ground, okay, because the gravity is acting on the object, that object then has potential energy, and this is described by the equation mass times gravity times height. Okay, so assuming projectile loses no energy from friction and there's no wind, use conservation of energy to determine the maximum height reached by the projectile and the velocity vector of the projectile when it's fallen through a vertical distance of 1 meter beneath the cliff edge. Okay, so we need to calculate the height of this point, which is the highest point, and the velocity vector when the projectile is at this point. Okay, well, the initial velocity vector, because it's at an angle of pi/4 and it's fired at a speed of 10 meters per second, it's going to be 10 multiplied by cos pi/4 in the x direction and sine pi/4 in the y direction. Okay, this just comes from if I was to draw a right angle triangle here. Okay, so that's cos of pi/4 and sine pi/4 is 1/√2, or if you prefer √2/2. So √2/2 times 10 is 5√2 in both directions. Okay, so the maximum height is reached when kinetic energy is equal to potential energy. Okay, so we have half mv squared equals mgh. Now we're only dealing with gravity, which points straight down, so we only need the y component for the velocity. Okay, the mass doesn't matter, so we divide. If we divide both sides by m, okay, so we've got half times 5√2 squared, which is 5√2 is going to be 25, okay, equals 9.81h. So if we rearrange and make h the subject, we get 2.5484, which is the maximum height. Okay, what about when it falls to a meter below the cliff? Okay, well, what's happened here is it's gained 1 mg for potential energy. So mgh is potential energy, but because it's gained 1 meter, okay, there's an additional mg contribution to the potential energy. So if we use kinetic energy, half mv squared equals mgh. Okay, sorry, that's the kinetic energy plus that's half mv squared, by the way, plus an additional mg. So g is 9.81 times m. Okay, divide throughout by m. Okay, so therefore we get rearranged to get the velocity come home in the y direction. It comes out at 8.34. Now, there's no force acting on the velocity in the x direction. So the velocity in the x direction of 5√2 is unchanged. Okay, so that's where that comes from. So the velocity vector, when it drops a meter below the cliff, is given here. Okay, part B is a different problem. You're told about a spacecraft which has mass 200 tons, is in outer space and doesn't act. It's too far away from any object for gravity to affect it, and it's travelling in this velocity. So it's a 3D, 3D velocity, and it's struck by a meteorite with a mass of 10 tons, so it's a lot smaller than the spacecraft, and that's travelling in this velocity. Okay, so the energy from the meteorite or collision is absorbed entirely by the spaceship, or the meteorite is absorbed entirely. Calculate the new velocity. Now what we have to do here is the conservation of momentum law. So this means the total momentum in the system, i.e. the spaceship and the meteorite, has got to be the same before and after the collision. So after the collision, we have the combined ship and meteor mass, which is travelling in our new velocity, which I called a v. So that momentum, mass times velocity is momentum, it's got to be equal to the sum of the momentum from the separate bodies. So the mass of the ship travelling with velocity u plus the mass of the meteor travelling with velocity w. So we know what the masses are, we know what u and w are, so we just simply plug them in, rearrange, and we get the new velocity. Okay, how much kinetic energy has been absorbed by the collision? So we need to calculate kinetic energy before and after the collision, so using half mv squared. Okay, so calculate for the spaceship, so half times v squared gives us 2 million joules. Kinetic energy of the meteorite, doing similar, gives us 1.45 million joules. Okay. Now if we do the combined, so our new velocity vector here, we use half mv squared for that. So the kinetic energy of the spaceship after collision is 1.4976 etc. joules. So the total energy absorbed, you calculate the distance, and that's down to 1.9